In this video, we're going to talk about the composition of two functions and what that has to do with limits. So what I want to do first is I want to talk about the image of a function, and let's let f be a function from g to c. The image or the range of a function, so whenever you hear the word range of a function, this is what they mean, but it's the set of all the values f of z, where z is in the domain g. So this is called the range of the function f. This second set here is called the codomain. The codomain can really be any set that contains the range. It can be the range itself. It can be the whole set of complex numbers. Just to be as encompassing as possible, usually we will write the set of complex numbers. But when we talk about functions, and when we're doing this very carefully in a mathematical setting, functions actually have three parts. There's the rule itself, like the f of z equals z squared, or whatever your function is that you're working with. There's the domain, and then there's the codomain. And changing any one of those parts can change the different properties that the function has, like whether or not the function's one-to-one, or onto, or whatever. So changing what those rules are can actually change all about the function. So it's better to think of a function as actually three parts. It's the domain, the codomain, and then the rule, whatever f of z is. And so typically we write z gets mapped to f of z. So like z gets mapped to z squared, or whatever f of z is. Now the image or the range is important when we're talking about the composition of two functions. And let me just kind of give you an idea here. Let's say that we have two functions f and g. I'm going to start using a E1 for the domain so that we don't have a capital G and a lowercase g. But let's let f be some function that's going to map E1 to the complex numbers. And let's let g be a function that's going to map the set E2 to the complex numbers. Then f of g of z is defined if, so this is, so I should say f composed with g is defined as f of g of z. And that's going to make sense if g of z is in the domain of f. So in other words, f composed with g makes sense as a function if the image of g, so if g of e2 is a subset of the domain of f or e1. Okay, so in general, f composed with g is defined if the image or range of g is a subset of the domain of f. Okay, so that's what needs to happen in order for composition to be defined, in order for that to make sense. Given that the composition of functions makes sense, we have the following proposition, and this will be very useful for us. So continuous functions are ones that play nicely with limits. So let's write this down. So let's let f be a function from E1 to C, and g is going to be a function from E2 to C. And suppose two more things. Let's suppose that the range of g is a subset of the domain of f, and that the limit of g of z, as z approaches z naught, exists. I don't care what it is. Let's just suppose that this limit exists. If f is continuous, so if f is continuous at the point L, where L is what this limit is, let's give this a name. So if the limit of g is z, if the limit of g of z as z approaches z naught is L, and if f is continuous at L, then the limit of f of g of z as z approaches z naught is equal to f of the limit of g of z as z approaches z naught. So in other words, the limit of f of g is equal to f of the limit of g if f is a continuous function at that point L. Okay, so what this says is that just like in Calc 1, continuous functions are functions that you can bring inside and outside of limits. Okay, and this is a very key feature of continuous functions that we use over and over again.